Might as well get in good practice.
Yeah.
So friends, a data set that's been kind of hiding in the background for the first couple weeks of this course we had together, the first half of the course, we were talking about like insurance, lack of insurance among 65 and older and things like that. Talking a lot about statistics, we're talking more about statistics. One of the more important numbers to keep track of is the number of people in our country. I mean, that's one of the things that as our country gets larger and larger and larger, we have to start making adjustments for. I know it's hard to see it, but the font's kind of small. Well, we'll take care of that momentarily. And that's part of the point is keeping track of the numbers like this is great, but it's also a little bit cumbersome because you have to digest. I mean, this data sheet goes down. I got this off the Census Bureau's website. I mean, it goes down to 2011, which is the most recent date. I got the source down here if you want it. So here's the population of the U.S. from 1900 on. In 1900, it was at about 76 million. And it's just gone ahead and picked up and picked up and picked up. And some of the things you hear are, well, when's it going to hit $500 million? Or when's it going to hit, $1 billion? And things like that. When is it gonna? At what point does our rate of uninsured exceed blah? Well, in order to know that, you have to know what your population is going to be. So these numbers are a nice baseline. I had to use something similar on a much smaller scale. I worked with the Bend PD about 5 years ago on budget numbers, and I had to bring in the population of Bend, which was very, very tricky because the population of Bend was exploding at the time that I was doing the numbers for him. So I gave him 5 or 6 different models. I'm like, dude, honestly, it's like spinning the carnival wheel to figure out which one of these fits because I can't predict it. What's fun about the U.S. population numbers are they're actually pretty predictable. Do you know how fast the U.S. is growing? It's a great question. No, good. That's kind of the reason I didn't either, which is why I collected the data. So what I did was I plotted the data. So what you see here, 1900, 1910, I didn't plot every single data point, I plotted every decade. So you get a trend of the shape from 1900 to 2010. 2020 I left out there as an extrapolation when you get to if you guys want to do it. So now the question is, what shape are those points making? Are they linear?
Linear.
Right, absolutely. You could definitely slap a line on there. Let's do it, shall we? All right, here we go. Let's do a layout. Let's do a trend line. Boom, there it is. And I think the best thing you can do, and this is where technology is freaking awesome. If you think it's linear, put a line on there and then decide if it fits or not. What do you think? What do you think? Yes, I'm seeing a couple of yeses and a bunch of no's. Chelsea, like, I don't know. Go why? Why don't you know?
Well, if you actually look at it, it looks like it kind of curves a little bit just because...
It's the Usain Bolt problem, isn't it? You can put a line on Usain's data, but the problem with it is it under or overestimates, and the problem with under and overestimation is it's doing it almost predictably. With linear data, it's not going to be perfect. This is one of the things that drives introductory stat students nuts is it never goes through the points. You're right, it never goes through the points. You're always going to have noise above and below it. But the problem is, when you put this line on here, these few are above, then these are below, and these are the most below, the ones in the middle of this little section, and then it goes back to being above. So there's almost a pattern in the data that's escaping the line. And that right there is a pretty good indication maybe it's not linear. Does that make sense? I'm not saying you can't put a linear amount on here, but here, hopefully this will be proof as to why it's not linear, okay? If I ignore the line for a second and just look at the first differences, if it were linear, there should be a pattern in my first differences. Hence, slope. There should be a slope that's relatively consistent. So what this tells us is the number of people we pick up each additional year. 1.5, 1.6, 1.5, 1.5, 1.7, 1.6, 1.6, 1.7, 1.7, 1.9, 1.5. Now that's not bad. But the further down you go, the more off it becomes. That's the trick. As you scroll down, look at these first differences, friends. Now we're in the 2 millions, 2.8, 2.8, 2.8, 3. Now we're in the 3s. It's varying too widely to look linear. Damn. So linear's kind of out. Sorry, Shelby. Not to totally can your idea, but it's not behaving linearly. Amber, go.
Does that take into account people who have died too?
The idea. Well, it kind of does, in that the idea of a census is it grabs those who are alive, so it won't grab those that are dead. I don't know if that's a good answer or not.
Oh, I see.
You see what I'm saying?
Just take into account people that are born now.
Essentially, you're picking either born or moving to the country.
Right.
So new Americans that are now counted in some way. Is that
Yeah.
if that's fair? Now you got to realize too, every 10 years the census actually tries to count them. The numbers in between are estimates. Because a census isn't done every 10 years. In my opinion, the census should never be done. It's a waste of federal dollars. The U.S. the census was great when there were like 20 people in the country. It was like you and like George Washington. Like, George, you still here? Sweet, 2, count it, check. I mean, that was awesome. But now there's like 310 million of us. And there's still the same number of politicians in Washington trying to do the census again. No, even the Census Bureau says, this is a dumb idea. We should do a random sample. And the politicians say, no, it's in the Constitution. Yes, the Constitution, I don't think, realized how big the country was going to be 200 years later. Maybe. I don't think so. They were awesome in a lot of ways. I don't think they realized the explosive growth of this country.
That's why they put in the ability to amend the Constitution.
Exactly. Why don't they? I think they're getting close on I think we're getting close on the census. I think we're getting close on that. But you're right. That was that's one of the best foresights that they could have possibly done. But, so I think we've ruled out linear. So it curves. I think Chelsea's getting exactly it curves, yes? So the next thing I thought was, let's put a parabola on it, right? So here we go. Let's get rid of the line. Let's get rid of the line. And let's put a parabola on it. Polynomial order 2. Looks pretty good, yeah? It looks pretty good. It doesn't look bad. But then I said, oh, wait a minute. I can check it algebraically. I can check it algebraically by looking at second differences. Remember the idea of quadratics, their second differences are constant. So curiosity killed the rule. Here are my second differences. What do you notice?
They're all over the place.
They're all over the place. They're not consistent. If it were quadratic, you should see some consistency. And I'm not saying perfect consistency, I'm saying some consistency, like my bike data. That was arguably quadratic because gravity is quadratic. But this sure as hell doesn't look, I mean, look, it goes from negative 23 to positive 404. It's a bit of variance. So, I said it's not quadratic, at least it doesn't appear to be quadratic. So I thought, okay, the model I tend to use the most in situations where I see a slight curve, where gravity is not at work, is exponential. When gravity is not at work, when gravity is at work, it's going to be quadratic, because that's just what happens with quadratic. Or that's what happens with gravity. But I said, let me try exponential. So what I did was, I said, all right, percent differences. I'm going to take this year's population, 1901, and I'm going to divide it by the previous year's population. So you see what I'm doing right now? I'm going to take 1901s and divide it by 1900s and see what the percent change was. In other words, not an additive change, but a percentage change. What do I have to multiply by to get to that next one? Not add. Okay? Okay, it's 1.02. Now that's a growth, not a decay. Everything we looked at so far is decay. That's a growth, yeah? Which means we picked up what? As a percent, how did the population of the U.S. change? From 1900 to 1901. What does the 1.02 mean? It increased by
1.02% people.
I love what you're saying. We got to get the decimal point in the right place. What does the 1 indicate? 100%. Which means that the original 76 million people we had are still there, or at least there are still 76 million people in the country. What's the 0.02? 2%. Remember the decimal point.
Oh.
0.02 is 2%. Which means we added 2% to the population of the U.S. from 1900 to 1901. We maintained 76 million, and this additional 1.5 million represents a 2% increase in the overall population. So 1% will be about 750,000 people. From 1900 to 1901, that will not stay constant, will it? As far as the 1.5 million will not always be 2%. It depends on the base unit each time. So let's analyze. Let's keep going. I'm going to drag that formula down now. If I drag it down a little bit, this right here, it looks like it's the same number, doesn't it? And it is, but look at the numbers it's dividing now. It's dividing 1902 by 1901. Still 1.02. Which means that it grew 2% from 1900 to 1901, and guess what else it did? It then grew 2% again from 1901 to 1902. Let's see if it continues. How about from 1902 to 1903? How about, let's keep going. Now, good. I love the holy moly. Thank you. Now, notice it did change. It changed a little bit in there. Somewhere in here we go from 1.01, 1.01, 1.01. It's always interesting to see what the changes are. Let's go over here to the years. 1915, 16, 17, 18, 19. What was happening? World War I was going on right then. Why would that affect the population? Soldiers going off. I don't. My history isn't smart enough to understand how that would impact this many people. How many soldiers did we send off World War I?
We didn't send anybody till 1917.
We didn't send in 1917, so maybe there was something else going on in that time period.
I would say it was probably harder for people to afford to come over to the U.S.
Maybe immigration was tougher then, potentially setting up for the Great Depression kind of thing, national economic scale, maybe. It could just be a random fluctuation in the system too. It could very well be a random fluctuation. It might only be a 1 or 2 year fluctuation whose ripple effect is felt for a while and then gets corrected for later on. Now watch what happens. Watch what happens. There's also a 1.00 right there, yes? 1.00. Let's keep going now. Let's drag this formula down. Here's World War II, right? Here's up to about World War II, 1945. Remaining constant at 1.01. So maybe the 1.02s were a little bit excessive in the beginning. Let's see what happens. Let's keep dragging. Oh, we corrected back to 1.02 now. Now I have a partial explanation for that one, I think. What happened after the war?
Baby boomers.
Baby boomers. That could potentially explain some of that increase in percentage. Or it could just simply be that the percentage was a little bit artificially low and just corrected back to its mean. Possible. Let's see what goes on. I also want to talk about one other thing too that we have to chit chat about. Okay, look, correcting back to 1.01. Let's keep it going. Look at this. Almost perfectly stabilizing at 1.01. So it almost seems like 1.01 is the trend. So 1% growth is the trend, and the 2% are a little bit more of an anomaly. There's a couple reasons for that. Can you think of any reasons why the 2% would be a little bit of an anomaly and the 1% is more of a stabilization? Any ideas, whether historical or mathematical? Any ideas?
I think there at the turn of the century too, we were in a pretty big sized industrial boom too.
Yes, and there weren't that many people compared to now. There was a quarter of the population. If you look at world populations, which I'm going to have you guys do in a quiz for next week, I've got some fun UN data. The population of the world doubles every 40 years. That's something to wrap your head around. If you go back in time, every 40 years the population of the world doubles. So we hit in 1960, I think it was 3 billion people, I believe. And then in 2000, it was roughly 6 billion. And now we're at 7 billion. Right around 2012, it was at 7 billion. Now to double again, we have to go to 12 billion. So that would be in 2040. I want you to plot the data and see if it's actually trending the way the UN is predicting that it trends. But if you reverse engineer it backwards, you basically lose half of the population of the world every 40 years if you go backwards. Therefore, coming forward, you double it every 40 years. Now that's unsustainable, obviously. We can't just keep doubling every 40 years. The Earth is a finite resource. More on that in about 5 minutes, because I do want to talk about what happens when exponential growth has to be checked. But right now, it looks like the exponential growth of America, which appears to be exponential, doesn't it? It doesn't look like it's getting checked, does it? It looks like it's pretty much growing at 1%, which might be our carrying rate. That might be our carrying rate of growth. So if we needed a model for this one, if we needed a model for the population of the US, I'm going to mute this for a second. I'm not going to have you guys scatter plot those data points, my God. Here's 100 points to put in your TI. We don't need to, do we? We've got them in Excel. Hello. There you go. If we've got them in Excel, we just ran the numbers that way. You don't actually have to scatter plot them. You could just run them like this. Experiment number 4. U.S. population. U.S. population. We don't even get the TI for this. We can develop a mathematical relationship. And we can use that to generate populations whenever we need it. It looks like this is the equation that we need. Now, what should we use for that first amount, that base amount? Remember what the first amount was? I don't. 76 million! Thank you. I'm going to call that my base amount, 76 million.
Was it billion or?
It was million. Oh God. Yeah, it's got.
Okay, never mind.
We had a mass plague around 1905. Wiped out 99% of our population, got us back down to where it should have been. 76. I'm just gonna put 76. That's okay with you guys. 76. And we'll make a note of it in the variables, that's in millions. 76 times 1.01 to the x power. That's our model. Where x is the number of years since 1900, number of years since 1900, where 0 would be 1900, and the y would be the population of the US in millions. Population of the US in millions. So if you plug an x value in for a number of years past 19, let's say you want to plug in 84 for 1984, it'll kick back the population. I went ahead and called that 1.01. Now, I guess technically speaking, I could go for like more of an average. I could average all those rates. But you mind if I just call it 1.01, 1% growth? Especially the more recent trend seems to be 1%. Oh, I forgot to mention something else in that data. Did you notice how there was a little hiccup around 1940? Some of that is definitely baby boomer stuff, but some of that also is the annexation of Hawaii and Alaska. That's when they became states-ish in that hop. So all of a sudden, you increase the population of the U.S. kind of artificially by the fact that we settled those states in the 1940s and 50s. So a little bit of artificial hops. Some of those 2% are a little bit fictitious. Only by mathematics it's up by 1%, but not really. I mean, but you see it stabilized itself too after another decade. It became more stable at that rate, and so the rate begins to show itself. So what this means is, each additional year we pick up roughly 1% of the population. Let's check it right now against the U.S. Census Bureau's data. You guys figure out what's the population according to this model. What's the population in 2013? While you look that up, I'll Google it. While you're crunching that in your machines, I'll Google it.